Now that we've actually studied solving the inequalities, the last thing left to do becomes very, very simple. And all we need to do now is graph the linear equalities, just like we graphed linear equations in Chapter 3. Instead of, excuse me, instead of showing the linear equation where all the answers simply lie on the line itself, we're now going to graph the linear equality to represent all of the answers that are contained in the solution set. And as we will see, that is a much, much larger number of solutions than simply lie on the line. There's going to be one small difference between graphing linear equalities and graphing linear equations. When we graph linear equations, of course, we have the equal sign, which means that we have a solid line and everything lies right on that point. Well, the only difference between inequalities and equations, as we saw before when we graphed them on the number line, was that when we had something that was a solid dot on the number line, when we graphed them on the number line, remember we had a solid dot, we have to have a way to represent this when we graph it on the coordinate plane, as we have down here. Well, that's very easy. Since we had a solid dot on the number line when we graphed it, when we put it on the plane, we're just going to use a solid line. The other difference was when we had an inequality that simply said greater than or less than, we had a hollow dot that was on the number line. Well, this becomes a little bit more difficult to represent on the plane down here, because when you draw a line, how do you draw a hollow line? Well, there really is no such thing as a hollow line, so the equivalent that we use is very simply a dashed line, and that's our equivalent of a hollow dot. These two things will be important to remember as we come down here and graph these things on the coordinate plane. But the rest of it's very, very simple, and the rest of it is exactly like we did back in Chapter 3. Okay, so very quickly, let's look here. We've got y is greater than 2x plus 3. We know from our previous studies that the slope in this number is the slope in this linear inequality is the number 2. So our rise is actually, because remember, slope is always a ratio of rise to run. Our rise is a positive 2, and our run is a positive 1. We always have to represent it as two numbers. And our beginning point, or more accurately stated, our y-intercept, where this equation is going to cross the y-axis, is the number plus 3 out here. So our b is plus 3. Okay, our line, how are we going to represent our line? Well, we have the inequality, which is simply less than. We know that if we graphed this, as I said before, on the number line, it would be a hollow dot. So when we graph it down here, what we are going to use is a dashed line. So our line is going to look something like this. Coming down here, let's change our color to orange to make it a little bit easier to see. We know our beginning point would be a plus 3, so we're going to start at the origin. We're going to come up here to a positive 3, 1, 2, 3, and our first point would go right here at plus 3. Remember, we need at least 2 points to draw a straight line. So our slope is what tells us where to go to for line number 2, point number 2. It's positive. We know our line's going to go up, so starting right here, our rise is 2. We would go up 2, 1, 2, and our run is 1. So we would go to the right 1 unit, and we would put our second dot right there. And then we, of course, have to draw our line through that. So our line is going to be, as we said, a dashed line, and it's going to go through the point. Let's use green for this. All right, it's going to be a dashed line, and it's going to go through these 2 points right here. So our line's going to look something like this. Starting right here at this point, it's going to come up here through the other point and go shooting off forever and ever that direction. And of course, it's also going to come down here, and we're going to shoot off for and ever in this direction. So our line's going to look something like this right here. But we're not quite done. If we were just doing a linear equation, this would be it, but it's a linear inequality, so we have to graph, we have to show all the numbers that are included in the solution. And it's not just these things right here, because it's y less than. Well, less than implies typically things that are below something else. So what we need to do to represent everything else is we have to shade all these numbers that would actually be below this line as well, or less than this line, which is everything below. So it's going to be all these things that are down here in this part of the graph as well. So everything that's going to make this inequality true is going to lie down here in this half of the plane, which is one of our new vocabulary words. If you look up on the board, you'll see we have the vocabulary words boundary and we have the vocabulary words half plane. Well, this plane goes on technically forever and ever in all directions. So when we draw a line anywhere on the plane, this right here, it divides that eternal plane in half. We have half of the plane here and we have half of the plane here. Hence the word half plane. The other thing that splits those things into a half is called the line or the boundary line. So the line that we have just graphed is the boundary that separates this half of the plane from this half of the plane. And those are our new vocabulary words. If you do not believe me that we need to shade everything down here, we can also prove it mathematically. We can go anywhere out here on the x-axis. So let's say we chose the point out here 5. Okay, so we would substitute the number 5 into our equation. 2 times 5 is 10 plus 3 is 13. So at the point out here 5, y must be less than the number 13. And clearly things less than the number 13 are all these numbers that are down here. For example, at this point we are at number 7. On the y-axis, 7 is clearly less than 13, so it lies down here in our shaded area. We could go through and we could say that we could put 0 right here at 0, x equals 0. 2 times 0 is 0, 0 plus 3 is 3, y is less than 3, must be less than 3. And clearly all these points down here are less than 3. So you can look at the less than and see that that implies things below, or you can simply prove it mathematically. The only hitch to that, for this thing to ring true, is that your y must be on the left-hand side of the equation, okay? If you were to flip it around and say y is greater than, let me correct that. If you were to say that 2x plus 3, put this on the left-hand side and flip the whole thing around and say greater than y, everything is still the same. There's no difference. You just have to remember that y is the smaller thing, so all of this stuff has to go down here. All right.